When Mitch asked me to speak here, I thought carefully about what to talk about. Surrounded by several great physicists and mathematicians, I focus more on a mathematical angle for this talk, and I hope everybody finds it interesting. This is something I've been thinking about, I'd say now maybe for 8 years since the discovery of twisted bilayer graphene, and I came at it a very different way, a critical way maybe. I hope you find it interesting, and I'll talk about some of our modern takes on trying to see some things in experiment, okay, though it's very preliminary. So this has been a long cast of characters. Some people are in the audience here. Oh, there's no laser pointer. Is this my pointer? Okay. So some people in the audience here, for example, Yue Cheng and Gabby, and some other people actually came through here, for example, Fabian. So I'm thanking everybody and my experimental colleagues as well to help me all this work become possible, as well as Daniele, who's also here. Okay, so where I'm taking you today, I'm going to start by thinking about the stability of Dirac points. Maybe you haven't thought too carefully about this question. But I'm going to start by thinking about this in 3 dimensions because we actually have some control and understanding. Okay, that's going to then bring me from 3D to 2D, and I'll think about the magic angle actually as a phase transition, an incommensurate phase transition, which I think some mathematical minds are starting to think about very carefully. And I'll then talk about how we're trying to observe some of these ideas in experiment. Okay. So let me ask this question very generally. So how robust are nodal semimetals in the presence of disorder or quasi-periodicity? And I really mean Dirac cones. So I really want to think about a density of states that is vanishing at the node. Okay? And I want to ask, is this stable? You can think of this as a gapless phase of matter, and you want to understand its stability. You want to understand the stability to perturbations. Okay? In 2 dimensions, disorder, this was chewed up for graphene, is marginally relevant, so on and so forth. 3 dimensions, you're going to see it's very subtle. So if you do this in 3 dimensions and you go through this argument, actually this was done by Eduardo Fradkin when I was a year old, okay? 1986, this problem was posed, actually, before he even knew the existence of these materials. And what he found, though, was followed by 1 loop RG, is you find that actually you think perturbatively this is stable, okay? And if it's stable, there should be a phase transition out of it, which 1 loop RG predicts, okay? And so this was the story, more or less when I started my postdoc. But then there was this rather brilliant work by Rahul, David, and Shivaji, which basically pointed out that all of that misses these non-perturbative effects of disorder, which could destabilize the semimetal, basically arguing that the Dirac semimetal is unstable in 2 and 3 dimensions. Okay, this question is very subtle, and a lot of people worked on this, and I'm not even going to get into all the references. I'm just going to mention some work on it. Okay, and here's some numerical study. We're going to take a lattice model, so we have 8 wild points, and we're going to add disorder, and we're just going to study this without thinking too hard. And when you do that, you can use the so-called kernel polynomial method, which a lot of people here are experts on. I'm advertising here. I have open source software if you want this, and I've written a recent paper with our esteemed organizer, Mitch. I mean, using a more sophisticated approach, you can get more accurate estimates of these computations without any additional effort. So if you do this, it looks at face value like the density of states is 0, and I have a phase transition, so on and so forth. But this is actually completely wrong. Okay, and it turns out there's actually an exponentially small density of states down here, which if you don't do it carefully, you're not going to catch. Okay. And so this exponentially small contribution, which you can see is system size independent and converged, arises due to inherently non-perturbative effects. This is a quasi-bound state due to that happens at the large disorder strength, giving you these power law resonances and destabilizing the semimetal. And you could show this rigorously via basically a proof by contradiction, where if it was stable, then it has to remain analytic, and if it's unstable, it has to become non-analytic, a phase transition. So you can directly compute this second derivative, and you can saturate this peak in system size and basically your KPM expansion order, which is the energy resolution. So this peak is saturated, so there's no phase transition. So the conclusion was as follows. Okay, basically, if you at 0 energy, there's no semimetal. There's only a crossover scale. Okay, and what we thought was a phase transition is actually just a finite size crossover. And we have a review on this, and there's a review of modern physics to appear later this year on this topic if you're interested. Okay, so with this in mind, we went to asking, how do I stabilize this phase transition? Okay, so how do I basically get rid of the rare regions but keep the detuning of energy levels? And we arrived at actually a quasi-periodic potential, which is going to be very much reminiscent, as we all know, of incommensurate twists, for example. So let me just take this as a toy model for right now. So I have a potential strength in wave vector and phases. This is going to be like my interlayer tunneling and my twist angle and my origin of rotation. Okay? And I'm going to take some very incommensurate wave vector, and I can do some tricks by taking my system size to be a Fibonacci number. I'm probably preaching to the choir in this audience here. Everybody knows this stuff quite well. But one thing you may not be familiar with is thinking about stability of Dirac states, which means that you're thinking about stability of plane waves. A plane wave is a localized state in momentum space, and I want to think about its stability. Okay? So I want to think about the IPR in momentum space as a probe of the stability of a Dirac node. And if I remain localized in K space, this will be constant. Delocalized will be 1 over the volume. And at a phase transition, you get this highly non-trivial, potentially multifractal exponent, okay? K from momentum space. So if it's nonlinear in Q, my wave functions will be critical. Okay. So you can now look at the density of states. So this is the quasi-periodic potential. The random problem is over here. And indeed, we get this. This is basically where the bands come in and invert, or the first magic angle. There's a second magic angle. This is the modern language. We didn't understand any of this at the time. You have 2 transitions, okay? Both of those are where the density of states becomes non-analytic. I'll get to that in a second. But they also correspond to delocalization of eigenstates. So these are wave functions truly becoming delocalized in momentum space, okay? So how do we describe this perturbatively at weak potential? So we can do perturbation theory, and you can see right away you start carving out gaps, creating mini bands, right? And indeed, we can show, we were able to argue, based on the absence of any rare regions, that this semimetal should be stable to infinite orders in perturbation theory. This is a conjecture, okay? And then we should be able to show you carve out a mini brilliant zone at leading order in the perturbation, okay? Fast forward a couple of years, Moiré, who's here, proved this statement rigorously. So the fact that this is a Weil semimetal stable to infinite order with no and basically the absence of non-perturbative effects was a rigorous statement, okay? So this has now been proven. And now you can look at these transitions, okay? And now this is where you start to maybe connect to the magic angle, because rho double prime is 1 over the velocity of the Weil or Dirac cone. So when rho double prime goes to infinity, the velocity is going to 0, okay? And so these 2 transitions that I mentioned are bona fide vanishing of the velocity. So let's just take a look at one of them. Here's this random model with rare regions. We can get this to be a real singularity by cranking the resolution up, okay? And what this tells you, the velocity actually goes to 0 in a universal fashion at this point, okay? And so this is really what I mean by a phase transition, because the density of states is inherently non-analytic. And it's telling me the velocity actually vanishes in a universal manner. Okay, so let me just summarize everything I've taught you so far. So I've showed you that quasi-periodicity has no rare regions of the potential, and thanks to Moiré, we can prove the stability of the Weil semimetal to infinite order. I then showed you, using numerics, there's actually a phase transition where this velocity goes to 0, okay? And I also showed that this coincides with the true delocalization of the wave functions of momentum space, because I had an truly incommensurate problem. So now let me bring us from 3D down to 2D, okay? So in 2D, as I said, this was already chewed up in great detail. If I had disorder, you would immediately say, aha, I have a marginally relevant perturbation, so you don't have any stability. But that's not true for quasi-periodicity. We know even in 1 dimensions, Aubrey-André, you have a stable metallic phase. So what this tells you is that you can go down to low dimensions and have the Dirac points survive that potential, just like Aubrey-André. So we can do the same thing. Let's go down to 2D, similar model. I'm going to go to graphene in a second. Okay, again, similar potential. And now we can watch this occur in the same way. So here my velocity vanishes, my density of states is generated, and my inverse participation ratio undergoes this delocalization. So it's the same phenomenology as 3 dimensions. There's no real distinction, though we can get into transport distinctions because of the marginal nature of 2D. And you can now look at the wave functions, okay? Here's my stable Dirac points. So the wave functions are localized in K-space. They delocalize as promised. They actually become truly multifractal. You can compute the spectrum. And then they relocalize. This is the inversion of the semimetal that occurs in TBG when you go through the bands. It's the same phenomenology. There's no TBG model yet. Okay, So if you put this together in a picture of WQ, you can do analytics, you can do perturbation theory. This is the green line. You have several magic angles. And we were having lunch, and Elio and I were having lunch. He was a postdoc with peers, and we realized that it was basically all the same thing as TBG in the sense of perturbation theory. So we followed Alan's approach, and we worked out, first of all, in a diagrammatic sense, you can do all this. Now, this is the leading order. Elio pushed this, for example, the fourth order. And then we also did the same for TBG, of course, which is already done. But when you start staring at these equations, you have, C3, C4. So these numbers just depend on details, okay? But you have Dirac cones and quasi-periodic potentials. The magic angle is a universal phenomenon, okay? And this actually led us to pointing out the magic angles also occur in twisted nodal superconductors, predicting that Bisco has a magic angle of about 3 degrees. Okay, so this idea of the magic angle, I want to argue, is very general, okay? It's not just for graphene at a special angle. Okay, so as I was arguing, these are very analogous to each other. And at this level, you're just seeing some details. Okay, so now we can construct a simplified model of chiral twisted bilayer graphene. This is simplified in the sense we could do really sophisticated calculations with relatively local hopping. So this is ignoring some effects, but you can still get a lot of the interesting physics. And so as you can see here, now this phase, again, has now been proven by Vieri and my colleague at Rutgers, Ian, basically showing that now for twisted bilayer graphene, away from the chiral limit, this metal is again stable to infinite orders in perturbation theory. Okay. So as I said, experiments are down here. Very much smaller twist angle. I'm just going to, small twist angle, and so the interlayer tunneling is much weaker than I'm thinking about right here. But let's just come back to that in a little bit. But here I can just take you through a cut, okay? And again, you're going to see the same phenomenology. So again, we have now a multifractality directly at the magic angle, okay? And you go back to being inverted. So this is, again, very similar phenomenologies to what I just showed you. The wave functions delocalize, all the same process occurs. Okay. And so if you start staring at these, the only difference was where the Dirac cones are separated. Here they're separated by a twist of theta. Here they're separated by pi. But again, emerging out of the same direction. So then following our work, McGill and his colleagues, this was in University of Lisbon, Technical University of Lisbon, they showed basically a much more general model. They took all the hoppings and parameterized it as such. And they also found that as you go through the magic angle, you get close to random matrix theory level statistics, and you get delocalized wave functions. So this is going beyond our chiral limit and showing that this incommensurate effects do appear if you take the full model. Okay. All right. So this brings me to posing a problem to our mathematical colleagues. I want to call this the twisted 10 Martini problem. So our 10 Martini problem is an almost Matthew operator. This would be p squared over 2m. I'm replacing this by the Dirac operator. And it's a two-dimensional, this should be a two-dimensional potential, delete the z. Okay? And then you can also formulate this for TBG, where you have now sublattice in 2 layers. So you have a gamma matrix, and then you have also some sort of quasi potential. But this is very much a general problem, which I know Vieri is thinking very carefully about. Okay, and this is going to bring me just to some conjecture. Okay, so let's think about how these gaps open as we approach the transition. So in what sense is it critical? So in quasi-periodic systems, when you have criticality, your eigen levels have to also become fractal. So we should expect that an infinite series of gaps will open when I go through this phase transition. How do I see that occur? So my leading order perturbation theory, pi over a minus q, that opens my first Brillouin zone. As I keep getting closer to that magic angle, I open a second Brillouin zone, which is another hopping process or tunneling process at a much larger momentum exchange. You can actually work this out indefinitely, okay? And you can figure out which process is needed at the next order. It's actually going to define a sequence. It's really beautiful, actually. And so you can find the relative momentum that's going to play a role, and that this AN has to satisfy the sequence where you go down in energy each case. What is that sequence? This is nothing but the sequence that satisfies this condition, which are the convergence of root 5. So we derived actually every order in perturbation theory that opens a gap. And so we predict here at the magic angle, this series is going to go indefinitely, and you're going to open an infinite series of gaps. Okay. which is what's happening in the Aubrey-André model, the transition. Okay, so how do I see this in some calculations? We can take minimal models that support these mini-bands. So here's my second mini-band. I've already showed you this one. Here's now a third mini-band. I can't support this until I have at least 55 sites. And my fourth mini-band, which appears at 17th order in perturbation theory, only appears at 233 as basically a unit cell. Okay, and this leads me to my conjecture, which is that an infinite sequence of mini-bands opens at the magic angle in the incommensurate thermodynamic limit. And I pose that to my mathematical colleagues as a conjecture, and I hope that I promise you at least 10 martinis if you solve it, okay? Twist, no twist, however you want it, So, but that's the conjecture. And now let's come to seeing this maybe with some more sobering thought. Relevance to experiments. So relaxation plays a very strong role. So seeing things that are this incommensurate with bilayers is a challenge. The other statement is that this might already be appearing, but the energy scales are so low, it'd just be maybe impossible to see an experiment. And as I was just saying, at a mathematical level, people are starting to really think about this very seriously. So maybe we'll see some really interesting results over the next couple years. So this brings me to how I'm trying to think about ways of probing this. Okay, and so I have basically one which is an idea and one with some data. So let's first start with the idea. And the idea comes back to actually thinking about vacancies in graphene. If you're not familiar with vacancies in graphene, these go into the famous model of the pseudogap model, where the vacancy actually gives you a local magnetic moment. It took a while to figure that out. But that magnetic moment is not a standard one like in a metal because you have the pseudogap. So if your coupling is too small, it does not screen the impurity. If the coupling is large enough, you become condo screening. You have this critical point between them. So one idea was actually using twisted bilayer graphene as a way to tune this gamma C, as I'll show you here in a second. But first, vacancies in monolayer graphene were demonstrated to exhibit the condo effect. Here's T over TK scaling, very nice data. And then this is data from Eva's group, where they're able to see STM observations of basically these vacancy states being associated with condo peaks. And it's actually rather interesting. It's related to the fact that you have a local curvature, which allows the sigma and pi orbitals to basically hybridize, which if you did not have a Gentile distortion, these things wouldn't occur. So it took, I think, people quite some time to figure this out. We want to now bring this to twisted bilayer graphene as a way to probe these underlying critical states. Okay, so Yue Cheng, she did this really tour de force work where one thing we were really worried about is if I put an actual vacancy, this is a true vacancy in twisted bilayer graphene, it may not couple to these very long wavelength modes. And so we actually did a careful ab initio study, and indeed we can show they can. And so here are basically when you put in a vacancy, you get this rather large John-Teller distortion, which I mentioned is important to get these sigma pi orbitals to bond or to hybridize. And so then once we understood that, we wanted to think about how do I put a vacancy into twisted bilayer graphene. And so what Yue Cheng realized is she could think about the distance at which it distorts the system and embed that into TBG, basically by extracting the local cluster environment and then putting it into the twisted bilayer system. From that, we were able to compute basically a hybridization function at that vacancy site and understand that if you change that local curvature, you can control the strength of hybridization over this scale. This basically allowed us to build a toy model, which we could solve in some rather sophisticated fashion using this kernel polynomial method, which you can combine with the numerical renormalization group, which we have done. And so I welcome you to take a look at that. This code is available, freely available. And when you solve this, what you find is that this is the pseudogap problem, okay? And at the magic angle, the finite density of states, so its instability occurs for infinitesimal condo coupling. And so you have a local moment to condo singlet phase transition that's tunable by the angle. So alpha is the ratio of tunneling to twist angle. And you can actually analytically derive, based on scaling theory, so actually you can just, using the fact that you know this critical point is of order when the bare rho naught JC is of order 1, and you know that rho naught is controlled by the velocity, and you have basically the velocity relation for TBG allows you to derive this linear relationship analytically. Okay, so how do I see anything critical? So what's actually known is that the condo temperature in multifractal hosts have a very large tail to vanishing condo temperature. So here's AA, and here's AB. AB feels that tail very strongly. AA, you have a really large density states from those 1A functions, so you don't feel it so much. But here, that multifractality felt quite strongly. So the idea is, can we see this large tail in the condor temperature? That would be a signature of these multifractal wave functions. We're far from getting there, but with our helium gun at Rutgers, we can make vacancies in TBG. And here's looking at actual defect states and starting to see some condor resonances at these defect states. OK. The last piece, motivated by all this work here, we really started to realize that multiple layers is where you get strong incommensurate effects. And so in my last piece of evidence, I'm going to try to take TBG and align it with HBN to either try to amplify those critical states or maybe make those states somewhat more critical. And that's the idea as follows. And so if we take TBG aligned with HBN, now you have Moiré of Moiré patterns, and it's a rather complicated problem. It's also very metastable. And so when you put down TBG on HBN close to alignment, it has a very strong effect. And so here I'm varying that relative angle, and you're going between a case where they're commensurate, where the two BZs match, and then you go to a point where they're very incommensurate here, okay, where it does not basically ever find any commensurate condition. And we basically arrived at this phase diagram. This is experimentally determined. So these lines are these basically rigid lattice conditions, okay? And you can basically let them relax within those lines. And as was shown by Daniele in this setup, it's actually quite similar to TTG if people are thinking about that. So this is TBG relaxed on HBN as a quasi-superior potential, solving the classical force problem. What you find are these very large domains at the Moiré of Moiré length scale, allowing these states to be stable. OK, so now this is the periodic crystal. What we also found are these so-called, we called them, after Eva talked to Paul Steinhardt for quite some time, we called them intercrystals. So these have basically, they're not allowed by, basically, they're incommensurate lattices, but there are no forbidden rotational symmetries. So a quasicrystal has to have forbidden rotational symmetries in addition to being on some incommensurate lattice. So these metastable lattices that we're finding all over the place don't necessarily have that rotational symmetry that's forbidden. Okay, here is this so-called dodecagonal quasicrystal. Okay, so I've now shown you two examples of incommensurate cases, intercrystal and quasicrystal. And now let me just show you a probe of trying to get some, basically, are the states critical? So what you can do is you can think of your inverse participation ratio with wave functions in terms of a local density of states following this work prior. And if you focus on this second mode, you go back to basically a scaling we already talked about. Okay? And we can now do this on the LDOS data directly, coarse graining, and looking at moments as you vary the bin size. So the L is basically the whole system. We can't vary L in experiment. We can vary the bin size at which we look at the image. And what you see when you do this, so here's DIDV, so we're close to the magic angle between graphene. And here is the data. So this is not a strong effect, but it's not non-zero. And so there's a question about, theoretically, can we predict this? So if you look at the normal crystals, you don't get anything. The quasicrystal and the intercrystal, it does pick up a value, but that value is a small multifractality. Okay? And with that, I'm going to conclude. And so this is a theory. This theory is underway. It's still being computed, so we can't report that yet. But I can conclude. So I hope I've demonstrated a connection between basically this disorder-driven avoided quantum criticality and the magic angle actually as a phase transition. That's, an incommensurate limit actually can drive an infinite sequence of gaps opening at the magic angle. That's a conjecture. And I hope we can see these in experiments in the future. So thank you for your attention.
Actually, the previous slide, how do you calculate the dimensionalities there? How did you extract this D2 out of experiments?
So what you do is you coarse grain. So you take your whole thing, you make boxes. And then each size is a box, and you coarse grain into one box. And then you compute these per box, and then you vary the box size. And then you can, it's basically a function of
So it's basically a Hausdorff dimensions or something like that.
That's exactly what it is, yes. It's like the Hausdorff dimension of your LDOS image.
Thank you.
Yeah, and as a comment, you don't have the phase So you don't know the phase of the wave function. So there are things you can't get from the experiment that you can theoretically think about.
If you non-dimensionalize the Bistritzer-McDonald model, I'll speak louder. If you non-dimensionalize the Bistritzer-McDonald model, is it not the case that the sort of shape of the bands, it's a function of the twist angle, but it's also a function of it's a function of the ratio of the twist angle to the ratio of the interlayer to the monolayer energy, right?
Yes.
So does that not mean that you could always pick some nice commensurate angle, and it just corresponds, you know, and the magic angle is just some choice of the strength of the interlayer energy?
Yeah, I mean, actually, Corey showed this in an experiment. I mean, they took an angle that was not the magic angle. They applied pressure.
Right.
So the angle is not a universal thing. It's totally set by the interlayer tunneling. So if you change the interlayer tunneling, you change the angle.
Right. So then how can anything depend on the incommensurability of the angle, right? If it really is a function of both of those things. Do you see my point?
Well, I showed explicitly that it depends on the ratio.
Yeah. Okay.
In a universal manner.
I agree. Yeah.
Let me show you a picture here. Here. So, you know, this is the tunneling versus the angle. So this color is the appearance of density of states. You know, all these are incommensurate calculations. If you do these incommensurate calculations, you could still generate states, but the wave functions won't delocalize. So you can still flatten your bands, but the wave functions will be good plane waves, always. And so the delocalization of the plane wave eigenstates is really a true property of the incommensurate limit. So you can make big supercells and make the velocity really small. That's always OK. But what I'm saying is actually if you take them truly to be incommensurate, the wave functions delocalize at the magic angle. That's the statement. In a critical manner, which is you know, is a conjecture, and we have numerics.
And you're saying that is okay. So now I'm on board. So,
okay.
And you're saying that is a physically measurable effect.
I'm saying it's very hard to physically measure, actually. And with 3 layers, we're going to get to the point where we can see these effects. Actually, that's my point. Is that 3 layers, we're definitely getting there. The vacancy, you know, it's a tail of a distribution. It's not a smoking gun, but that tail would still be non-trivial to see. So I'm starting to hope we can get to there. Yeah, absolutely.
Hey, for small w, its linear relation is pretty good.
Absolutely. There's several magic angles that, you know, are coming out here that are all basically linear. You can't see them very well on this scale, but they come out linear. And then the curvature is due to, you know, this is 4th order perturbation theory, for example, that red line. Sorry, green line. So it just matches the, you know, and that's just like the middle of the region where we're saying, you know, the analytic magic angle is the middle of this little phase, you know, and experimentally, so we can show that this vanishes like theta cubed. And so, you know, you're at 0.11 eV, it's just a tiny little thing. You're never going to see it as a phase. You'd see it as a point in experiment always. You would never see that as a phase. Unless you could, you know, push W to be larger and then tune the angle. But, or maybe just look in, you know, 3 layers. And I think we're already seeing some of these effects. For example, I can just mention that since I have a second. Put this picture here. This is an incommensurate transition if you think about this as the IPR. It's just now you're seeing it at the level. To the Moire scale, we can see it in experiment. I'm not sure if we'll ever see the TBG criticality. I don't know. So yeah, I don't have a strong opinion actually.
Yeah, very beautiful. Going back to the beginning part
Yes.
of your talk, when you distinguish between disorder, you don't have to go back there.
Sure.
When you distinguish between random disorder producing rare regions and quasi-periodic not producing,
Yes.
giving a phase transition, therefore presumably not producing, right?
Yes.
So, can you say a little bit more about the mathematical reason for that? I mean, there are many cases in which quasi-periodic is sort of like random. I could think of a distribution and so on,
So,
is it really that because it's quasi-periodic, you get magic backscattering that cancels out some of the effects? Or
so the argument that we had in the paper, I mean, Vieri's here, so he mathematically proved it.
Yeah.
So I think he should comment on the precise. But I mean, the intuitive argument that we had is that you can't get an order. Every fluctuation of the potential has to be order 1 because it's infinitely correlated. That's quasi-periodic potentials are infinitely correlated, and so that argument led us to saying, well, unless you do something special to the number theory, there's no way you could get fluctuations beyond of order 1. That was the argument, which in any random potential, you can get around that because you can always make a cluster big enough where you can get to a large enough critical disorder above the value you need to be to bound the state. So that was our argument.
But does that mean there's a sort of, this is one of these ridiculous meta questions, but that if I add a weak disorder to the quasi-periodic model, is there something interesting in how quickly it goes wrong and I generate density of states at low energies?
Absolutely. Yeah. There's an interesting interplay. And actually, we have a paper on the 3-dimensional problem with disorder and quasi-periodicity if you are interested in.
Okay.
And you basically can think of the quasi-periodicity, if you're away from the magic angles, it redefines a new lattice with a new length scale. And when you add disorder, you'll get rare regions on this new length scale. And we were able to show that you get these basically emergent length scales at the Moire, and then the disorder physics then plays the same role, but on a much larger length scale. I know Vieri wants to comment on the stability, but you're going to speak tomorrow, right? So.
Any other questions? I actually have a question. So as we saw earlier today in the experiments, you have always a bunch of different angles, twist angles. It's never one unique,
Yes.
and it's a distribution. So how realistic is it to expect a truly incommensurate structure when there's always a commensurate angle nearby?
I would play it the other way. I mean, how do you think you're ever going to get commensurate when all the angles are mainly incommensurate, actually, right? Because you're talking about an irrational list versus a rational list, so the irrational list is much denser. So it's actually the opposite.
But in that sense, it would be hard to say that you hit the incommensurate angle. And given the fact that there's always a variation of the angles, the actual situation experiment is that the whole system is much more flexible.
Yes, absolutely.
Specific incommensurate value.
That's why I was saying relaxation could destabilize some of these results. So relaxation, I completely agree with you. So relaxation, though, is also, that's a little bit different than commensurate, because you're moving things around to be commensurate. So yeah, I'm with you. It's a good question. Thank you.
Well, thank you. Well, let's thank all the speakers of a very interesting session.